In this lesson, we're going to cover properties of logarithms. To start out, let's first review properties of exponents. We have here, if I raise any base to the power 0, I get 1. We can see this when we look at something simple, let's say 2. 2 to the third power, 2 times 2 times 2 would give me 8. 2 to the second power would be 4. 2 to the first power is 2. But 2 to the 0 power, remember mathematics is all about patterns. So if we're looking over here with these exponents, if I start at 8, how do I get to 4 from 8? Sure, I could subtract 4, but let's talk about multiplying or dividing, because exponents are repeated multiplication. 8 divided by 2 would get me 4. 4 to get to 2, I could divide by 2. And we could even expand this upward. 2 to the 4th, 2 times 2 times 2 times 2 is 16. And to go from 16 to 8, again, we're dividing by 2. So if I want to continue this pattern of dividing by 2, 2 divided by 2 would give me 1. And that's how we have a to the 0 power equals 1. Any base to the 0 power equals 1. Since we're talking about exponential functions and logarithmic functions, and we only discuss positive bases for exponents and for logs, we're going to take that a to be positive numbers. So any positive number raised to the 0 power will give us 1. Even though it's not part of this list, if we expand this even further to talk about negative exponents, what does it mean when I have 2 to the negative 1 power? I'm continuing that pattern of dividing by 2. So 1 divided by 2 would give me 1/2, and that's how we get this negative exponent to mean a reciprocal. Expanding it even more, 2 to the negative 2 power, we could look at this as 2 squared to the negative 1. That's 4. 4 to the negative 1. And again, we're dividing by 2 to get to the next number. 1/2 divided by 2 would get me 1/4. And then hopefully by this middle expression, you can see the 4. 2 squared is 4. And then that negative exponent means take the reciprocal. These exponents have a pattern, and we need to maintain that pattern throughout all of our numbers. So a to the 0 equals 1, and we demonstrate that here with 2 to the 0 power. The next one that we have is a to the first power equals a. Sure, 2 to the first power equals 2. Now these aren't terribly revolutionary as far as math goes. Exponents tell us how many of the number that we have that we're multiplying together. So a to the first power, we have 1a that we're multiplying, except we're only multiplying by 1. We're not really multiplying it by anything because we only have one of them. So a to the first power equals a. And for this particular case, I have associated logarithm properties for these properties of exponents. The first two that we're going to talk about, log base a of a equals 1. So this first one actually connects with the a to the first power equals a. And I can write this by saying that's my base a to the exponent of 1 equals the a that's on the inside. So remember that logs are exponents. Logarithm says what exponent of a gives me a. And I'm doing it in different colors on purpose so that you can see where the a's are coming from in our log equation example. Log base a of a equals 1 because a to the first power equals a. It's a direct relationship between those properties of exponents above. For the second log property, log base a of 1 equals 0. And this is because a to the 0 power equals 1. And this directly relates to that first property of exponent. So first two properties of exponents directly correspond with two of our log properties. These remaining 3 down below we're going to talk about in a little bit, so don't lose them. We'll come back to them. Some more properties of logs that we have that exist in number 3, we have 2 inverse properties for logs. And so inverse properties of logs say that if I have a positive base not equal to 1, then log base b of b to the power x equals x. I'm going to zoom in on this so we can see it a little bit clearer, especially with my colors. I can turn this log equation into an equivalent exponential equation by moving things around. And we practiced this in the last lesson. Moving things around, I take the base b and I raise it to the other side of the equation, x for the exponent, and that needs to equal whatever's inside the log argument. And we do indeed have equality, b to the power x equals b to the power x. We can do the same thing for this second property, b to the power log b of x equals x. But instead of rearranging it so that it's a log equation, I'm going to look at it in a slightly different way. Log base b of x is the exponent of b that gives us x when we put it in there. So b to the exponent of b that gives us x will give us x. So when we put that exponent in for b, we get x. Now this is all fine and dandy, feels like a little bit of hand waving. So let's go back to our first section in this chapter where we talked about inverse functions. So inverse functions, we looked at f composed with f inverse, and we looked at f inverse composed with f. In both of those cases, if we compose a function with its inverse, we will get back x. The functions I'm using for this, we'll use f of x is log base bx, and f inverse can be b to the power x. It doesn't matter which is f and which is f inverse. They are inverses of each other. So if you switch them around and say f inverse is the log and f is the exponent, it doesn't matter. We'll get the same result. So for this example, circle f inverse. If we plug in f inverse x, we'll have f of f inverse is b to the power x, which means we get log base b of b to the power x. And essentially what happens is the exponent of b that gives us b to the power x would be x. Or log base b of b to the power x, when the log and the base to an exponent get together, they cancel out and we're only left with the exponent. We can do a similar thing over here with the f inverse composed with f inverse with f of x. This will give us f inverse with log base b of x. And then f inverse is b to an exponent, and that exponent will be log base b of x. And then because we composed a function with its inverse, we end up with x. Alternatively, b with a log in the exponent, the b and the exponent of log cancel each other out, and we're left with just the argument. This idea of inverse functions, they're undoing what the first function did. And so by undoing, we're just left with our input. And that's why over here, these inverse properties both equal x. When we start solving these equations with exponents and logs in them, we'll be doing a lot more with the inverse properties than we will in this section. Let's talk about change of base. When you look at your scientific calculator, whether it's on your phone or using Google in the website, whether the calculator is a physical calculator in your hand like the scientific Texas Instruments calculator or a Casio calculator or anything that's scientific calculator. And scientific, I'll show you what I mean by that. We're really looking for 2 specific buttons for our algebra class. Or it's the scientific calculator on your phone when you turn it into landscape mode. A scientific calculator is primarily identified by 2 buttons that show up. Make my circle a little bit bigger. And that is the log button and the ln button. The log here, this is log base 10, And then this ln is log base e of x, or we rewrite that as ln. And we can tell this simply because of what their inverse functions are. The inverse functions are the second functions on that same button. You can see for log, the second button is 10 to the power x. So we have an inverse relationship here. And then for ln, we have e to the power x. There's an inverse relationship there. And that's how we get our log functions in our calculator. But we could have logs of any positive base. It doesn't have to be e or 10. We could have log base 2, log base 5, log base 8, log base 1.3. So many different possibilities. Infinitely many possibilities for our bases for logs. Well, we don't have infinite number of buttons. So how do we manage that? Well, it turns out that there's something called a change of base formula. So our calculators find logs with base 10 or base e, but we could have other logs. How can we find the values of those logs just by using our calculator? It turns out we can rewrite any log in terms of any other base. And this is the change of base formula. It looks a little complicated, but I'm going to break it down for you. Specifically for log base 10 or natural log. So we could say for log base b of a, this would be equivalent to log base 10 of a over log base 10 of b. So this is base 10 because I don't have any base on the log expression, on the log operation. There's no base there, so I know it's base 10. I could also say log base b of a is equal to natural log a over natural log b. It turns out that these proportions of logs give us our change of base. For the example, find log base 7 using your calculator. We've got two different ways, the common log, which is log, and the natural log, which is ln. So log base 7, here's the big idea. We're going to say common log, log of 7 over log of 3. Notice the argument goes on top and the base goes on the bottom. This is important. So argument on top, base on the bottom. And then we can use our calculator to determine what that value is. And pulling up my own little scientific calculator built into my computer. I've got my log and ln down here on the bottom left corner. And my calculator, the Windows calculator, we have to do things in reverse in a way. You'll have to work with your calculator to understand how you input operations like logs and exponents in. So start with something you know the answer to, double check and make sure that you're comfortable entering in the operations. I know that my calculator does this reverse notation, so I'm going to enter in the 7 first and then hit log. And you can see up top I've got log of 7. And then I'm going to divide by, put in the 3, and then hit the log. And so log 7 divided by log 3. What's showing right now on my calculator is just log of 3. It's not my answer. I have to hit enter to get the answer. So 1.7712 approximately equal. The value keeps going because it is irrational. And so that's how we would use the common log. Doing that very same problem into the natural log, we'll do natural log over natural log. We're going to put the 7 up top and the 3 on the bottom again. So argument on top, base on the bottom. I'll pull up my calculator. Let's see if we get the same answer. We should get the same answer. So we'll put in, clear it out first, 7 natural log divided by 3 natural log. And we hit enter. Hey, 1.7712. ... The exact same answer. This will work every single time. It's one of the beauties of logs is we have this relationship between them. And it really all comes down to exponents. In our next lesson, we'll cover the other 3 properties of logs that we have and show how those will be used to simplify log expressions and also expand log expressions into expressions with simpler argument. And although we won't be using the expansion more than just a practice of exercise, you can use expansion of logs into calculus classes where you have to do more with the log. And it can make doing calculus with logs a lot easier if you remember expanding logs. So Next lesson up will be the remaining 3 properties of logs.